Hello everyone, my name is Gregory Wilsenach. I'm going to be talking about some joint work with Anuj, Dawar on symmetric arithmetic circuits, specifically lower bounds for symmetric circuits for the determinant. So the brief summary of what we're going to be talking about today. Previously, in an ICOP paper, indeed in ICOP 2020, we introduced this notion of a symmetric arithmetic circuit, and we proved an exponential lower bound for the permanent in this model and a polynomial upper bound for the determinant. And the notion of symmetry in this context requires that the circuit remain essentially unchanged under simultaneous row-column permutations to the input matrix of variables. So we have a matrix of variables as input at the top of the circuit, and we allow simultaneous row-column permutations of that matrix. And each permutation needs to extend to an autonomous of the circuit, needs to keep the circuit unchanged. And in the paper today, the paper I'm going to be talking about today, we introduce a more stringent symmetry requirement. Namely, we discuss the action of the alternate group on the rows and columns of the matrix separately. And in this model, we prove an exponential lower bound for the determinant. And this importantly contrasts with the polynomial upper bound we have for the other symmetry group. Now, a fortiori, this gives us an exponential lower bound for symmetric circuits relative to the full symmetric group of the determinant, right? Which is a sort of more, in some sense, more natural group to consider in the determinant case, and we get a nice lower bound. It also establishes an exponential separation between two distinct and interesting symmetric arithmetic circuit models. In other words, different symmetry models for different groups. It sort of establishes the importance of considering these two different groups. The result is that it requires a substantial new machinery. So this includes developing new game-based characterizations as well as new ways of constructing particular types of matrices using Cypher-Ullmann constructions and a whole host of other things. So there are a lot of new developments in this context. And most importantly, perhaps, at least hopefully in the longer term, this result involves developing an entirely novel framework around how to analyze symmetric circuits relative to some different group. The result is that we can now study symmetry as a sort of resource and ask questions about how symmetric a circuit needs to be before we can prove some bound. So I'm going to discuss circuits very briefly. So everyone should be familiar with these. So a circuit is just a DAG structure, and here on the left-hand side you can see the input gates in green and the internal gates in blue and red. And in the Boolean context, we ordinarily have input gates labeled by variables and internal gates labeled by Boolean functions. So internal input gates could also be labeled by 0 or 1. And the idea is that a Boolean circuit computes a function in the following way. We take some input and assign them to the input variables, and then recursively evaluate each gate in the circuit until we finally evaluate the output gate, and that's the value of the function. And in this way, a family of circuits can define a language. In the arithmetic context, things are a little bit different. It was noted that a large number of algebraic problems can be reduced to the problem of computing some polynomial, or indeed, more accurately, family of polynomials. And in this context, we consider circuits that are slightly more syntactic in the way that we approach them. In particular, we generally don't. The input gates in this context can be either variables or elements from some field, not just 0 or 1. And we ordinarily don't replace the variables with elements of the field and evaluate. Rather, we just recursively evaluate through the gates, and treat the operations at each gate as field operations. So as ring operations in the polynomial ring. So ordinarily the gates are labeled by plus and times, and we can just recurse as normal, but in this case, again, we don't really replace usually with values. In this way, each gate defines some polynomial, and the circuit as a whole defines some polynomial at the output gate. Now, in this context, perhaps the two most important functions that anyone considers are the permanent and the determinant. So Valiant's conjecture, the analog of the P versus NP problem, the VP versus VNP problem, is equivalent to proving exponential lower bounds on the permanent. And indeed, the permanent and determinant, and in contrast, the determinant is perhaps the two most well-known functions in this context are the permanent and the determinant. The permanent is complete in VNP, making it one of the hardest problems that we tend to consider in this context. And the determinant is complete, albeit in a different sense, in VP. And as such, the VP versus VNP problem, the analog of the P versus NP problem, is often reframed as the permanent versus determinant problem. Why is it that the permanent seems so much harder than the determinant? And so proving lower bounds about either of these functions is proving, well, lower and upper bounds, but proving lower upper bounds for perhaps the two most important functions. Perhaps the two most important functions in this context are the permanent and the determinant. The permanent is the canonical difficult function. It's VMP complete. And the determinant is VP complete, albeit in a different sense. And as such, the VP versus VMP problem, which is the problem of separating these two complexity classes, the algebraic analog of the P versus NP problem, is often reframed or thought about as the permanent versus determinant problem. Why is it that the permanent seems so much harder than the determinant? And indeed, you can see below how these two functions are defined. The determinant and the permanent seem very similar in structure. The determinant just has this additional sign flipping. And so it's a sort of great mystery to try to prove exactly why it is that the permanent is so much more difficult to actually compute. And a lot of work goes into trying to understand these two functions. Now, one approach to understanding them is to look at restricted circuit models. And the reason for that is that we don't really have any superpolynomial lower bounds for general arithmetic circuits computing the permanent, or indeed for the determinant, but in the determinant's case, we have upper bounds. So we tend to establish them in terms of some restricted classes. So a very famous example is that there's no solid exponential family of monotone arithmetic circuits computing the permanent or the determinant, and the same for depth 3 arithmetic circuits, although here we have to put restrictions on the field. Now, what we're introducing, or indeed what we introduced in ICAL 2020, is a symmetric circuit model. So a model of what it means to be a model of symmetry in this context. So we say a circuit C is G-symmetric if the action of each permutation sigma in G on the input gates extends to an automorphism of the circuit. Let me give a somewhat concrete example. So here we have a circuit where the input gates are labeled by X, Y, and Z. And we want to consider this, to what extent the circuit might be symmetric. So let's consider just the transposition XY. Now, if we were to transpose XY, does this permutation extend to an automorphism of the circuit? And it's not too hard to see that indeed it does. If we swap those two gates, we just need to swap those other two blue gates, and indeed we have an automorphism of the circuit. So this circuit is symmetric with respect to the group generated by that transposition. It's not too difficult to see that indeed this particular permutation, the one in yellow, doesn't extend to an automorphism of the circuit. So this circuit is not symmetric with respect to any group that contains sigma 2. So before I move on, I need to discuss this previous work on on symmetric arithmetic circuits. In this work, we have two main results. We have a lower bound for the permanent, which establishes that for every field of characteristic other than 2, there's no family of sim-n symmetric arithmetic circuits over F of sub-exponential size computing the permanent. And here by sim-n symmetric arithmetic circuits, we mean the simultaneous action of the symmetric group on both the rows and the columns. Right, and we have a similar upper bound. Here we have to consider fields of characteristic 0 explicitly. In this case, it's for the determinant, of course. And here we have a size bound of O(n) to the 4, right? So we have a nice polynomial upper bound. But at this stage, you might be asking, okay, great, these seem interesting, but there's this sim-n, why sim-n symmetric? Why particularly this group action? What makes this interesting? What makes this canonical? And indeed, in the lower bound case, it doesn't seem to matter much. In the lower bound case, a fortiori, this lower bound applies to any group that contains sim-n, so any larger group action, which includes in particular the full symmetry group of the permanent, which is a much more natural group to consider, and indeed a whole bunch of other groups one might consider. So in the lower bound case, while the group choice may be arbitrary, it applies to all sorts of much more canonical groups as well. In the upper bound case, this is a bit more of a problem, and certainly this upper bound doesn't apply a fortiori to the full symmetry group of the determinant, and so it's a bit of a tricky question to answer. Why is this group canonical? And indeed, what we're going to be addressing today really carries on from that, and is sort of motivated by that question. So what we've done today is proved, in fact, that there is an exponential lower bound on the determinant when one considers the action of alt n cross alt n on the input gates, right? So here we do have an exponential lower bound. And now, of course, this lower bound does apply a for ri to the full symmetry group of the determinant. So we now do actually get an exponent, that any family of circuits that are symmetric with respect to the full symmetry group of the determinant is necessarily going to have to be at least exponential size if it's computing the determinant over Field's characteristic 0. We also get a lower bound for the permanent, a very similar lower bound for the permanent, but I'm going to be omitting details on this lower bound in this talk. So before we go on to actually discuss the proof techniques, and I'm going to have to apologize in advance for the fact that things do get a bit technical in discussing those proof techniques, because in some sense that's where the meat of the paper lies. I'm just going to briefly discuss two utterly crucial tools that we need to be able to prove lower bounds. So firstly, supports. Now, any lower bound for symmetric circuits, and indeed for symmetric linear programs and all sorts of other symmetric subfield or approaches in complexity theory rely on some theory of supports. So a support for a gate G, and let's suppose this, so support for some gate G in a circuit, and let's suppose the circuit has, say, a matrix structure on the input gates, and let's suppose G is some subgroup of some n. So we have some gate G and we have some G acting on the circuit. So a support is some subset S of n, such that any permutation that fixes S pointwise is also going to fix G. Right? So what exactly does that mean? So let's take a look at this circuit. And here we have some group G acting on the input gates. And let's again assume that G is a subset of a subgroup of some n, for the sake of simplicity. Now, if one applies G to those input gates, it's easy to see that if we fix x1 through x4, x11 through x44, and all of those gates are input to G, then definitely any permutation that fixes those is also going to fix G. Right? And as such, we might say 1 through 4, 1, 2, 3, 4, is a support for G. Right? That's the sense in which we mean it. So if we fix those guys over there, everything, we've definitely fixed G. And indeed, there's the important thing we want to do in the theory of supports is prove bounds on the size of these supports, right? So what we have is that if a family of alt n cross alt n symmetric circuits, Cn, where each circuit takes as input a matrix of variables, has sub-exponential size, then every gate in every circuit has a support of sublinear size. Right? So if the circuits are small, we have small supports. The next crucial ingredient is the bijection game. So the original bijection game, this is Haller's bijection game, involves two players, the duplicator and the spoiler, who play on a pair of graphs, GH, using k pairs of pebbles. Now, the duplicator is trying to show these graphs are similar, and the spoiler is trying to show that they're not the same. And the game proceeds in rounds with 3 steps in each round. First in the round, the spoiler picks up a pair of pebbles, AI and BI. Now, these might have been originally placed on the graph, or they might have not yet been placed on the graph, on the graphs. The duplicator then picks a bijection, let's say gamma from G to H, such that this maps AJ to BJ for everyone except the pebble we've already picked up, right? So it's mapping the pebbles accordingly. And the spoiler then places the pebble that he picked up somewhere and he places the AI pebble, anywhere on G, and he places the BI pebble on the corresponding vertex in H. Okay? The spoiler wins if duplicator has failed to, if gamma fails to be a partial isomorphism between the pebbled sets, the pebbled sequences. And we say duplicator is a winning strategy if he has a way of playing forever. Now, the generalized bijection game, and before I get on to the generalized bijection game, I should say that there's a connection there between bijection games and counting width, and indeed counting logics, which I'm not going to go into now. I'm going to go straight to the bijection game and frame that all in terms of supports. But I would recommend reading the paper for a discussion of the counting width angle or approach to describing it as well. So in the generalized bijection game, we again have the duplicator and the spoiler, who are playing in the same way. The only real difference is that we also specify a particular collection of bijections from which the duplicator can select. Right? So the game again proceeds in 3 rounds, except now the duplicator must select from that set of bijections, and we continue as before. Now, what's the difference here? Well, one obvious one is that if we're playing on, say, pairs of isomorphic graphs, in the previous case, the duplicator could always find a function that mapped from, that ensured that the two graphs were, that he could play forever, so he had a winning strategy. In contrast, in this context, it might be the case that the isomorphism that the duplicator would like to play to make sure he can play forever isn't actually in the collection of allowed bijections. So it might be that the spoiler can win for a particular set. So that's where the distinction enters. Now, importantly, and we generally don't specify the set of bijections directly, but instead specify a single bijection from G to H, and then a group of permutations on G, and just by composing, we get, of course, a collection of bijections. And indeed, in this paper, we are actually interested in often just taking a single graph and then taking a set of automorphisms directly. So the connection between the two is a little bit long to frame. And here I framed it in almost exactly the way we're going to use it today, rather than in the slightly more general way it appears in the paper. But essentially, the crucial thing is the following. We have a sequence of graphs. If there's just a sequence of graphs, which can be bipartitioned into two partitions of size n, and here I explicitly say 1 through n and 1 through n because we want to feed these, we want to treat these as input to a circuit, and so we need to actually have labels for the different vertices to do so. And I'll brush over the details of how this is normally treated. And so if we have this family of graphs, such that the duplicator can win the bijection game with the set of bijections generated by the group alt n cross alt n and some alpha, with 2k pebbles, then any family of alt n cross alt n symmetric circuits that distinguish the two copies, the two graphs, right, gn and some alt gn, which is really just a different representation of the same graph, must have gates with all supports of size more than km. In other words, if the duplicator has a winning strategy for the game with 2k pebbles, then it follows that any circuit that distinguishes these two representations of the graph must have more than k supports of size more than k. Right? All gates must have all supports of size more than k. In particular, if you place a linear lower bound, if we can prove a linear lower bound on the if we can ensure the duplicator can win the game with a linear lower bound on the number of pebbles, it follows that any circuit that can distinguish between the two graphs must also have a linear lower bound on the size of the supports. So what does that mean if we bring it all together? Well, we want to prove this main result. How do we go about it? Well, from the support theorem, we know that any family of any sub-exponential size family must have sublinear supports. So if we show that there's a sequence of bipartite graphs such that the duplicator can win the bijection game with a linear number of pebbles, then in particular, it follows that any circuit that's computing this family must be exponential in size. So let me go back. So what remains to do in this discussion, is to actually establish that family of graphs Gn. And that's what the rest of this work is going to be. We're going to be spending the vast majority of the rest of the talk actually constructing the sequence of graphs Gn, and then finally playing the game very briefly, or at least sketching out how the game is played on these families on these graphs.
So we begin with a construction that might be familiar to some people, the Seyfert-Immermann construction. And how this works is we begin with a 3 regular bipartite graph, and we construct this graph xg by essentially replacing each vertex with a gadget. And you can see the gadget here on the right-hand side. So you replace each edge with a pair of vertices here, f0, f1, g0, g1, h0, h1, and then we have these internal vertices. Now, it's easy to note that xg is bipartite, and importantly, we're going to be interested in in the biadjacency matrices that you can construct from this graph, right? This XG. And of course, to construct a biadjacency matrix, you need to choose bijections from the different partitions. In other words, you need to order each partition in order to construct the matrix. Now, importantly, and reasonably straightforwardly, we should recall that if M is a biadjacency matrix of some xg, then any transposition applied to the row or column negates the determinant. So if the determinant of M is the determinant of M is the negation of the determinant of N, where N is formed by flipping two rows or two columns. So what we're going to be talking about is how we're actually going to prove, right? We'd like to construct, remember, this family of graphs, and we need to make sure that in this family, in the sequence of graphs we're going to construct, that we're going to have one graph Gn and one graph alpha Gn that have different determinants. Now, as I noted a moment ago, if the determinant is non-zero, then we can construct, we can take alpha to just be a flip of a row or column, and now we have Gn and alpha Gn, and they're both going to have different determinants. So we want to find some way of making sure the determinant is non-zero in Gn. And we're going to do that by going through a whole process of first counting perfect matchings and showing how perfect matchings relate to the determinant, etc., etc. And this is what we're going to be discussing in the next few slides. So let's let M be the biadjacency matrix of some CFI graph xg. We identify a perfect matching. This is a perfect matching in xg with a bijection A to B denoting adjacency. In other words, the bijection maps little a to little b if A and B, if the edge from A to B is in the perfect matching. And of course, then just rolling out the definition of the determinant, right? We get that the determinant is equal to this particular formula here. And what we're going to do is consider two types of perfect matchings. We say that a perfect matching mu is uniform if for every edge in the underlying graph, this is the graph from which we construct the CFI graph, there's at most one edge from a vertex in one gadget to the other, right? Otherwise, we say it's non-uniform. So let's look at an example. So here you can see that for every edge, right, for every F0, F1, G0, G1, H0, H1, there's only one edge between that and the adjacency gadget, the adjacent gadget that gets chosen in the perfect matching. So this is going to be a uniform perfect matching. And if indeed there were two yellow lines from, say, F0 and F1 away to another gadget, then it would be non-uniform. So let's look at uniform, non-uniform perfect matching. So let's consider non-uniform perfect matchings first. Now, let's suppose we have a non-uniform perfect matching, and we remove two vertices matched outside of the gadget, right? Remember, non-uniform perfect matching is going to have two vertices that are matched outside the gadget. You can see the example up here. And let's suppose you actually remove those two vertices that are mapped outside of the gadget, right? Because they're matched and we want to consider matchings and the rest of it. Now, it's possible to show that in this 8-vertex graph that remains, each matching that can appear can be paired off into matchings of opposite signs. And as such, we can actually just remove the non-uniform matchings and really just consider the determinant in terms of the uniform matchings, right? So we can prove that, in fact, the determinant is equal to this uniform case. And here by uniform xg, I mean the set of all uniform perfect matchings on xg.
So now we need to move on to actually talking about how we're going to count these uniform perfect matchings. So let's suppose mu is some perfect matching in the Symmetric graph. And let's let f mu be the set of edges in the underlying graph such that exactly one of the corresponding edges in the CFI gadget corresponding to that edge in the underlying graph is in mu. And let f mu be the function that essentially tells you which one of these two edges in the Symmetric gadget is actually being included in the perfect matching. Now we can sort of go in reverse. Let's suppose we have some two-factor f and some function f, and let mu ff be the set of all matchings which in some sense match that template. In other words, such that f mu is equal to f and little f mu is equal to f. Right? In other words, as I said, match the template in that sense. Right? And the theorem we have is that the set of all perfect matchings that match that template. So these are perfect matchings in the CFI graph that match this template. Is 2 to the 2m, where m is the size of a partition of G. Right. So to actually see this, let's take a look at a diagram. Right. So to see this, note that suppose we have some matching in FF, and in that at some gadget, and let's particularly zoom in at some gadget at V for some vertex V in the underlying graph. And notice that exactly 2 vertices must be matched outside the gadget, because remember, we're interested in uniform matchings. Right? So in this case, let's suppose that F0 and G0 have been matched outside the graph. Now we can delete those vertices because we're interested in the other matchings. So let's delete those vertices. And now notice we have a 6 cycle. So if you look at the top there, if we delete F0 and G0, we in fact get that 6 cycle at the bottom. It's not quite a 6 cycle, it's a 6 cycle with a path leading out of it. Right? And it's not too hard to notice that has exactly 2 matchings. And it follows that each vertex we can it follows then that at each vertex we can independently select from those 2 matchings. Since there are 2m vertices, right? Since there are m vertices in particular in a partition of G, it follows that they're going to be 2 to the 2m perfect matchings that actually satisfy this template. So we now come to one of the most important parts of the paper. Establishing that in fact the Symmetric graphs for an important class of graphs are going to have non-zero determinant on their bijection matrix, of course. And so what we do is show that if a graph has an odd number of perfect matchings, then in fact the determinant of the Symmetric graph is going to be non-zero. And before we do that, we need to make a few observations. So firstly, it's easy to see that for any 2 matchings in mu FF, they're related by an even permutation and so have the same sign. It can also be shown with considerably more work that the sign, in fact, doesn't depend on F. Right? If we swap out F, and I'm talking about small f here, we always get that all the perfect matchings in that family have the same sign. Right? And so now we're ready to prove the theorem. Right? And as I said, if Gn has an odd number of perfect matchings, then the bijection matrix of the Symmetric graph has non-zero determinant. This is the crucial result. And let's quickly go through a sketch of that argument. We recall that since we can cancel out the non-uniform perfect matchings, we can write the determinant. We can write the uniform, or we can write the formula for the determinant in this way. Right? Now let's suppose f is some 2-factor, and let mu f be the set of all matchings, all perfect matchings, in the template mu f small f for any particular choice of small f. So we don't care about which labeling function we have on the edges, it doesn't make a difference. And using the result we had previously, we can recall that it follows that the size of this set, right, the set of all perfect matchings irrespective of the choice of little f, is 2 to the 4m, right? And it's not too hard to see, following from this, that the determinant is given by this formula. What do I mean by sin f? Well, recall that that all the perfect matchings in mu f are going to have the same sign. So sin f is just the sign of any perfect matching within that class of perfect matchings, right? And this is just implementing the above formula, right? But recall that the number of 2 factors in a graph that's 3 regular is the same as the number of perfect matchings. In fact, the complement of every 2 factors is a perfect matching and vice versa. So you have this bijection between 2 factors of perfect matchings. And remember, that set is odd by assumption in the theorem. So it follows that this summation is going to be a summation of a bunch of -1s and 1s, but the number of summons is going to be odd, and so it follows that this sum can't be 0, and therefore the determinant can't be 0. And that's the rough idea of how. That's not too rough. There's some detail there, but that's the detail on the proof. We're now going to talk about actually how we go about constructing these graphs that we're going to ultimately use to play the games on and prove our lower bound. Now, the graph constructions are going to mostly be built around the 3 things we've spoken about already. We need to make sure the determinant is non-zero so that we can ensure that we have a pair of graph representations with different determinants. we need to make sure the graphs are well built so we can use a CFI construction, and we also need to make sure the graphs meet certain conditions so that we can actually play the game on them. So firstly, we're talking about balanced bipartite graphs. That's where this condition comes in. We need to make sure the graphs are 3 regular, necessary for CFI construction. We need the graphs to be what we call k-well connected for some linear bounded k. And what we mean by k-well connected is that any balanced separator has size more than k. And for the reasons mentioned a moment ago, we need Gn to have an odd number of perfect matchings. And that's the determinant condition, right? And we prove this by showing that a random 3 regular bipartite graph on 2 to the n vertices satisfies the third condition with high probability. And then we show that it can be modified to satisfy the fourth condition while still keeping the connectivity condition high, right? So we can still satisfy the connectivity condition in some sense. It's still, you know, we might diminish k, but not so much that we lose this linear lower bound. That's the idea, right? And to do this, we need to use some facts about the distribution of 3 regular bipartite graphs. And again, I won't go into technical detail about what we actually did in this context, but I'll sort of just hand wave us through. Well, not hand wave, but I'll try not to go through too much onerous detail. Okay, and so let's talk about sampling and expander graphs. So the trouble is that sampling a random graph and distribution, right, the uniform distribution the uniform distribution for 3 regular bipartite graphs is not exactly easy, but it is well known to be approximated by other distributions. And so what we consider is this distribution Gn, curly Gn, defined by the following procedure. So this is how we pull a graph from this distribution. Firstly, we choose uniformly at random the bijections pi1, pi2, pi3, right? And U and V are supposed to be the two partitions, right? The partitions of this, the bipartitions of this graph. And we check that these functions are pairwise disjoint, right? We need to, of course, ensure this so that the resulting graph is 3 regular. And if it's not the case, we discard bijections until it is the case, right? And we get a graph defined as follows, right? So in other words, each edge is defined by one of those permutations. And importantly, this distribution is contiguous with the uniform distribution on 3 regular balanced bipartite graphs on 2 n vertices. And what that means is that since any graph in uniform distribution is an alpha expander with probability tending to 1, we can say the same for Gn. Indeed, that's what contiguous means in this context. It means that anything that holds any property that holds almost surely for one class will hold almost surely for the other. Now, lastly, we note that if a graph in Gn is an alpha expander, it follows that it's an epsilon n well connected for some constant epsilon greater than 0. This just follows from the obvious connection between the expansion given for expanders and the balanced separators in the graph. So let's next talk about perfect matchings and rank, right? So I mentioned there's that fourth requirement that we actually have to make sure that we can ratchet up the just going all the way back here. We have to be able to ratchet up the number of perfect matchings whilst not hurting the connectivity too much. And we do this in terms of rank, and let me explain how. Right, so we've gotten the first 3 conditions using this probabilistic argument. To get the fourth, we need to pick a graph with an odd number of matchings. And so let's suppose G is chosen from Gn, and let AG be the bijacency matrix for this graph, or a bijacency matrix for this graph. And we should like with high probability that the permanent of the matrix over F2 is not 0. It's the same as saying it needs to have odd permanent. It needs to have odd permanent. Now, why am I suddenly talking about the permanent? Well, recall that the permanent of the bijacency matrix of a graph is equal to the number of perfect matchings in that graph, right? So that's the connection why I'm suddenly talking about the permanent. So to get this oddness condition, we just need to check that the permanent as a matrix over F2 is not 0, right? But let's recall something. We're talking over F2, and the permanent and the determinant coincide over F2. So it suffices to show that AG, the the bijacency matrix, indeed has non-zero determinant, which is to say it has full rank. And how do we go about showing that this matrix has full rank? Well, we show this in 2 steps. We show that with probability bounded away from 0, the rank of AG is at least n minus some sublinear factor, right? Which doesn't quite get you there. We also need to actually, we couple this with another result, which says that if we have some graph G with sublinear rank, we can transform it into a graph G dash with slightly higher rank, and G is well connected. If G is well connected, then so is G dash. More formally, we actually lose a little bit of the connectedness feature, but since we only need to iterate this a sublinear number of times, we still can retain a linear lower bound on the well-connectedness parameter. But I won't go into too many details there. So how do we then put the graph together? Well, we have a sequence of bipartite graphs. We want to have a sequence of bipartite graphs with these conditions, as we just discussed. So let M and N be two biadjacency matrices of the CFI graph on Gn, where N is, for example, formed by swapping a single row or single column. It should say or, not and there. That's a typo. Although, well, no, it has to be or. The fourth, and what this fourth condition now guarantees is that the determinant is non-zero for both M and N, right? But of course, M and N have inverse determinants, right? And so therefore they have non-equal determinants. So now we have a family of biadjacency matrices, or we can think of these as just ways of representing these graphs that have different determinants. And it now suffices to show that duplicate is a winning strategy in the bijection game. So how do we actually play the bijection game? Well, let's first talk about what we actually want to prove using the bijection game. So we play the bijection game on two copies of XGN. So we can think of these two copies as essentially two different biadjacency matrices, or we can think of them as two copies of the graph, where Gn is chosen to have the required four properties, and we just discussed how we can ensure that we have a Gn that has the required four properties. And with a set of bijections, right, these are the bijections we're going to play the game with, is given by this, again, this pair where the group Alt A cross Alt B and alpha, right, where alpha is essentially just a transposition that swaps, say, two elements of the two columns, right? So alpha is what kind of introduces this twist, and which is what negates the determinant. And indeed, it's possible to show that for some at least linear function, the duplicate is a winning strategy in the bijection game using that number of pebbles. Right, so how do we actually play the game? And again, this is actually quite a detailed argument in the paper, and I don't want to go through it. I don't think we have the time or space to really go through it in an awful lot of detail, but let me provide something of an overview. So the important thing is to note, and it's kind of one of the crucial factors when we're talking about these gadgets, is that there's an automorphism of the gadget that swaps the pairs of vertices in each of two pairs of outer vertices and fixes the vertices in the third pair. Right? What do I mean by that? So here's the CFI gadget floating around, right? And the idea is that if you give me any two pairs, say F0, F1, and G1, G0, right? There's an automorphism that swaps those two and fixes the third, right? So for example, here's a case, right? So if we swap G1 and G0 and F0 and F1, here is the automorphism of the group of the gadget that keeps those that extends from that particular those particular transpositions. And H0 and H1, you'll notice, stay still, right? An essential idea behind the game uses this feature, but let me discuss how the game works, right? So the idea is that it suffices for the duplicator to maintain an automorphism of the graph formed by composing some transposition, say G0, G1, with a member of Alt A cross Alt B. And we think of this transposition, this G0, G1, as representing something like a twist in the graph, or if I'm trying to be specific in the representation of the graph, say in the matrix. Right? And so the spoiler should like to reveal this by placing pebbles around the twist. And so what the duplicator does is avoid that by essentially hiding the twist. Now, what does that mean? Well, Gn is k-well connected. So if you removing all the vertices corresponding to gadgets with one of the k pebbles still leaves us with a two-connected component, delta, that's at least half the size of Gn. Right? So we have this large two-connected component, even if we remove all the vertices that have been pebbled by the spoiler. We're talking about the pebbles, the A1s through AKs. So now the duplicator can effectively hide the twist in the large component and use the fact that the component is too well connected to move the twist along a cycle. And remember, cycles have even length, and so this suffices for our work, right? We can move between bijections, and we can do so in a way that involves just applications of even permutations, right? And that suffices ultimately now to get our main result, because now we've played the game on the graphs. The graphs have different determinants, and therefore we've satisfied the conditions to prove our main result. So let me talk a little bit about let me make a few concluding remarks. So the approach to take here not only proves an interesting result, right, an exponential separation for the determinant for two interesting symmetry-restricted arithmetic circuit models, as well as, of course, proving a lower bound for the proving a lower bound for the canonical symmetry model for the determinant, namely those circuits that are G-symmetric, where G is the full symmetry group of the determinant. But it's worth noting that in this talk I've tried to be quite explicit and talk about the alter n cross alter n group action, because we only really have time for that. But in fact, the machinery that we develop in the paper goes well beyond that. It's usually agnostic to the group actions. Not always. There are some places where it's not. And indeed goes well beyond matrix structures on the input, right? We can talk about graphs, and indeed we can talk about really general structures, just essentially G-sets being taken as inputs. And as I said, there are some limitations on what we can prove at this point in terms of generalization. So if we could generalize the support theorem, we'd be able to prove all sorts of interesting results about symmetric circuits, far more general versions of symmetric circuits. And it's important to note as well that this approach, and indeed especially if we manage to prove general results of the support theorem, really opens up the opportunity to study symmetry not as some sort of tacked on feature, but as a real resource for understanding computation in general, right? How does symmetry trade off against computational power of the model, and allowing us to change the group of the group and the action that we're considering, what the circuit is symmetric with respect to, really allows us to move along a spectrum from the trivial group action, where we're just talking about normal arithmetic circuits, all the way to other group actions at the top, like alter n cross alt n, or sim n, or other group actions you might consider. And it's really interesting to think what happens as we slide along the scale. Can we begin to prove lower bounds along the scale? We already have an exponential separation for 2 points on the scale. That's what's proved in this paper. But can we go further and really understand this spectrum? That, I think, would be a very interesting next step. Anyways, thank you so much. Really appreciate your time. And I hope you all have a lovely conference.